All right, so we're going to finish up this chapter and then try to blaze through as much of the next chapter as possible. It's a little dry, the next chapter, because it's a lot of biochemistry, and biochemistry is chemistry based, and so I'm going to show you tips and tricks on how to do that biochemistry as we go through that chapter. So back to the histology of the large intestine. We have no plica there. We have no villi. We have no microvilli. So we're not trying to increase the surface area because most of the absorptive features that we need have been taken care of in the small intestine. However, we have lots of water still with the fecal, what is now our fecal material inside the large intestine. And so we need to actually absorb water and the various ions that are actually always associated with our fluids such as water. Additionally, we have no enzymes because remember, enzymes are actually for chemical digestion, and so that's not the feature of the large intestine. And we are going to have all kinds of goblet cells here with our simple columnar epithelium, because that's where we find goblet cells with simple columnar. Even if it's pseudostratified, it's still considered simple columnar epithelium. And I hope that you can see the goblet cells in the histology picture here. They're the ones that are very pale in coloration, and they're all over, and their job is to produce mucus. And why would we want to have mucus as part of the layer of our large intestine? It's not like the stomach. We don't have a bunch of hydrochloric acid that we have to protect ourselves from. So why do we produce a lot of mucus here? It's lubrication for fecal material, correct? And so those mucus cells are indeed producing mucus, a nice slimy layer, because slimy, if things move along a slimy layer so much easier than a layer without slime, so to speak. And so that's what the mucus is there for. Now, transit time of the fecal material in the large intestine is so variable. Everybody has a different transit time. And what I mean by transit time is the amount of time it takes for the material to go from the cecum all the way into the rectum and the anus. And if you have a long transit time versus a short transit time, you will have two very different types of bowel movements, correct? A long transit time means what type of bowel movement versus a short transit time? Long means it's in there a long time, and what do we know about the water if it's in there a long time? It's absorbed, that's right. So that means more likely the individual can develop constipation with a long transit time. And a short transit time means it's not in there for very long, so that our ability to actually absorb the water from the fecal material is diminished, because the time that's there is very important for the absorption of water. So that individual will actually have more of a diarrheal type of pattern with their bowel movements. So that's an important difference, because everybody has a different story, and as you age, the stories get more vocal. That's what I notice. So it's one of those things that I guess, since I don't have problems with constipation, I guess constipation is very difficult for many people. The other thing to realize, when you have constipation, remember those haustral contractions that will actually predispose the individual more for the condition of diverticulosis. Did we talk about diverticulosis last time? Okay, so diverticulosis will actually only occur in the haustra, not in the tennae coli. And part of the reason why diverticulosis, that's a condition of, versus itis, which is inflammation of. So diverticulosis is a condition of, and diverticulitis is inflammation of the diverticulum. Well, a diverticulum is basically a herniation that has occurred through the outer wall of the large intestine. And so it will have the mucosa associated with the lining of the herniation and various layers of the large intestinal wall, except for the outer smooth muscle layer, because that's all gathered up in the tennae coli. And it's easy to have these problems occur in the haustra because they are not as well reinforced, correct? So we lack our reinforcement with the outer longitudinal layer of smooth muscle, and therefore that makes that area more subject to inadvertent herniations. one of the things that's important with any sort of herniation, whether you have an inguinal hernia or some sort of umbilical hernia, you have to have increased intra-abdominal pressure or intraluminal pressure to cause the herniation. And so you actually, with the large intestine, when you get the diverticuli, you have fecal material in there. It clamps down on, the haustral contractions clamp down on that fecal material, and if it's really hard, it makes it more likely to have a herniation to occur, and that herniation itself is called a diverticulum. And so a single one is a diverticulum. Many are diverticuli, remember nucleus, nuclei, and the condition of all these herniations is called diverticulosis. Most people don't know that they have hernias. Hernias themselves are not uncomfortable or painful until it becomes inflamed, which is what diverticulitis is. And the only other time that people actually realize that they may have diverticulosis without actually being symptomatic is because they had a colonoscopy. Because if you take the fiber optic light and scope and stick it into somebody's large intestine, you go along and you see, oh, look at all these little Swiss cheese holes that are actually in there. The holes lead into pockets, so to speak. And if the pockets get fecal material that is actually kind of hard or difficult to get out, then that predisposes you more likely to actually diverticulitis. So people know they have a problem when they hurt. And the hurting is itis, not osis. Makes sense? Okay. So that's the story of diverticulosis. And when you guys do your system review of our female cadaver at the end of the semester, she has some diverticuli. And she has it in the area that is most commonly associated with that. And let me ask you a question. Since I told you it's most commonly associated with constipation, would the diverticuli more commonly be at the beginning of the large intestine, the middle of the large intestine, or at the end of the large intestine? The end. And she has it exactly where I'm just referring to. So do be sure that you actually take a look. A long time ago, we had a cadaver, also it was a female specimen, and her large intestine looked like Brussels sprouts. She had so many diverticuli that I got, what is wrong? And then I realized, oh my gosh, this is the worst case of diverticulosis I had ever seen in my life. But it wasn't adhesed to any of the surrounding tissues, so she never ever had that I could figure out itis, diverticulitis, but she was at super high risk for that. So I knew without a doubt that that person had a certain condition of their bowels, and that person had constipation. And so that's why they actually talk about high fiber diets are very important, because that actually helps to smooth out the contents, and the intraluminal pressure does not get to be excessive as we move things along. So it's very important fiber in the diet for a healthy colon. Digestion in the large intestine. Our notes state almost all nutrients have been removed by that time, and that's true because that's what the small intestine is for. The small intestine is to actually finish off any sort of chemical digestion we need and to get the material inside the cells from the lumen. So that's part of the small intestine, its main feature for us. One of the things that we will have with the large intestine is it is designed to absorb water. And even though we don't have microvilli and things like that, that's part of what we were just talking about, absorption of water as well as ions. We will also get some vitamins absorbed in the large intestine, and that is because they are produced in the large intestine by our colonic or fecal bacteria. And these are some of our B vitamins and vitamin K. And it's important that you recognize that there's a difference between vitamin K and potassium. What's the difference? Whenever I draw potassium, what do I always include with it? A plus charge. And so whenever you see K, it is vitamin K. When you see K plus, it is potassium. So that's just something to make sure that you guys realize, because I can see where people would not be sure whether or not I'm talking about vitamin K or potassium. And always whenever I talk about potassium, I talk about it in its ionic form, or else I spell out the word potassium. Motility of the large intestine, very slow segmentations that we call haustral contractions. So remember segmentation, clamp, clamp, munch, munch, munch in between. That's the muscle of the wall actually doing it. And that's actually, those haustral contractions actually are part of what causes the diverticulosis, because it's contracting down very strongly in high intraluminal pressure. Mass movements are the term that we use for peristalsis in the large intestine. Remember peristalsis, we're moving the material down? Well, we call it mass movements when we're in the large intestine. And it says here in our notes, slow, powerful contractions that propel contents towards the rectum. And we actually only have 2 or 3 a day of these. And it's not unusual for them to actually occur after a meal. And so some people know, who are working with children or geriatrics, who have a tendency to become constipated. Children become constipated because they don't want to go poo because they're busy playing. So the more you hold it, therefore the more water gets sucked out of it. Okay. Well, for geriatrics, they have lack of physical activity, correct? And physical activity is also very important and healthy for normal gut motility. And so because geriatrics are very sedentary, they don't have that physical activity that also helps to have normal gut motility, so they are also more prone towards constipation. Anybody that's prone towards constipation should go to the bathroom after they eat a meal, because their gut naturally wants to move. And so if you can actually get the little kids that have this tendency to go to the bathroom and say, okay, you know, dinner's done, I'm washing the dishes, you know, hey kiddo, time to go to the bathroom, and they'll look at you, I don't have to go. I said, go anyway. You know, go sit down on the pot, and it's amazing how many times, at least 50% of the times, they'll poo for you. So that's a pretty good number whenever you have kids that are having problems with their bowel movements. Defecation is brought about by baroreceptors. So stretching of the rectal wall will initiate a reflex called the defecation reflex. This will cause an automatic relaxation of our internal sphincter. Plus contraction of muscularis externa, of the sigmoid and rectum. And you have to voluntarily relax the external sphincter in order for this reflex to finish its process. And so that's where sometimes you feel like, oh, I got to go to the bathroom, but oh, I can't, not right now. And you've had a meal, for example, and you're in class, and you know, and you're into a hot topic that you don't want to miss out, like something about the bowels or something along that line. And so you're not going to leave, and you're contracting that external sphincter, and that's okay, because then that defecation reflex will be like any other smooth muscle process. Because that's why we like smooth muscle, because you can distend the organ that has the smooth muscle walls for a while, and it will, and you can tell it no, no, no to the contraction of it, and it will go, okay, you know, I'll calm down for you. And then you can fill it up a little bit more, like our bladder that we do, and then suddenly you'll be getting nerve signals that you need to go to the bathroom, and you say no, 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 and then it will say okay for a while, but everybody knows after a while you have to respond to its request. So. And for parents, they love it that when their kids can learn how to actually manage the defecation reflex, because it means that they don't have to worry about, you know, a bunch of depends or things along that line. So I call them depends, I guess. What do you call the ones for the kids now? Pampers and Huggies and all that good stuff. But when I say depends, you also know that what I'm referring to. Big diapers, little diapers, big diapers. Landfill material, which is actually really not good. Okay, so we're into the physiology of digestion and absorption, and now we're into the terminology enzymatic hydrolysis. What does hydrolysis mean to you? Water cut. And so when you hear the term hydrolysis, I want you to realize we're taking a large molecule and we're making it smaller, right? That's what cutting it is going to do. And we're going to use enzymes for this process. And in addition to enzymes, water, because what happens, the way I liken it to, you take something and you cut it in half and you've got what I call raw edges or ends to it, and you need to seal them off. And what's really cool is when you use water as part of the cutting process, we also break the water molecule up and put it on the ends of the new two molecules that we actually have where we made the cut. So we are using enzymes and water. So hydrolysis, water, cutting. So we are making things smaller with this. But realize our main topic here is we are interested in the enzymatic process here. Because one of the things that is not an enzyme is hydrochloric acid. And we are using hydrochloric acid to make things smaller, but right now we're actually more interested in the enzymes that we're actually using to make things smaller, to break them down into the size that we can actually absorb into the cell itself. So breaking down large molecules into monomers, which are the size that we can actually utilize to bring into our cells. CBH, that stands for carbohydrates, so you have another abbreviation for another word. And the monomers of carbohydrates are monosaccharides, or simple sugars. Now, the ones that you most commonly think of for the simple sugar is glucose. But don't forget fructose and galactose. So those are our simple sugars that we actually have for carbohydrates. The enzymes to work on carbohydrates actually start in the oral cavity. And remember the enzyme for carbohydrates in the oral cavity? Amylase. So oral cavity. Amylase. So that's where actually our enzymatic work on carbohydrates actually begin. But it's not a lot. And with amylase, what we're going to do is we end up with a disaccharide. A disaccharide's two sugars, and that's what we actually have taste bud receptors for. So we actually can appreciate the sugar, disaccharide sugar taste itself whenever we break things down with amylase. Now, the disaccharide is maltose. Then we get into the small intestine. And we'll encounter more amylase, but we will also encounter maltase, sucrase, and lactase. And you know those are all enzymes because they have the ending ASC. And you can pretty much tell what they're supposed to act on by the prefix that we see. Maltase, maltose, sucrase, sucrose, and lactase, lactose. And so those are our enzymes for carbohydrate hydrolysis itself. Now, these enzymes will be found throughout the small intestine and will then help us break things down into the monomers, which will then allow us to bring the substance into the cell itself, into the cell's cytoplasm and contents. Proteins, you guys were great, knew that the monomers for proteins were amino acids, and so we started our protein digestion in the stomach, right? So protein digestion starts in the stomach. And what's the enzyme responsible for protein digestion in the stomach? Pepsin, yes. That's why I wanted to make sure you know hydrochloric acid is not considered an enzyme, so that's why we're specifically on the enzyme action of things here. Now, remember, in order for pepsin to be most active, it has to be in an acidic pH, so that acid is very helpful in the activation of pepsin. But then in the small intestine, we will encounter trypsin and chymotrypsin. And so those are also examples of protein digesting enzymes, and they are in the small intestine. Breaking our proteins down into the amino acids, which we can then bring into our cells with all that extra microvilli helping us with that. Then nucleic acids will undergo nuclease activity, and so it depends upon which nucleic acid that we're working with. This will give us our nucleotides to give us. Nucleotides are our monomers of nucleic acids, and so we actually have one called deoxyribonuclease, and we have another one called ribonuclease. So those are the ones that are actually easy to remember. These also are in the small intestine, where we're having this type of enzymatic activity. As far as we're concerned, lipids really don't start any significant digestive enzymatic activity until we get into the small intestine. And the enzyme for that is lipase. So lipase is going to help us break down our lipids into the various monomers that we have to make them into in order to actually absorb them. And what's really strange is that lipase, as it states here, is going to break our triglycerides, which we typically abbreviate TG, into monoglycerides plus fatty acids. And remember, triglycerides are a glycerol backbone, C. It's a 3-carbon thing, the glycerol backbone is, and we have 3 fatty acids added on. And so when we treat this with lipase, we get a CCC plus 1 fatty acid still attached. That's why it's called a monoglyceride, plus 2 cleaved fatty acids. We break a couple of bonds and we end up with our monoglyceride and 2 fatty acids. So this is really interesting. Lipase is taking our TG and putting it into what looks like an incompletely digested product. And we still have to get then this into our cells. And in order to do that, remember, we always pre-treat our lipids with bile, an emulsifier. So must pre-treat with bile. And remember, it's the bile salts in bile that is the emulsifier. And our cartoon here is actually showing you this. So up above, close to the gallbladder, we see some lipid droplets going down the small intestine. We see we're adding some bile salts to this, and we're going to do segmentation. We're going to mix things on up, and then we are going to coat them, the fat droplets that we're going to make smaller and smaller, with these bile salts. And this size that we get them down to, we call those little bitty pieces that are now fat coated with bile salts, we call them micelles. The micelles then come into contact with the microvilli and are then the fatty contents, the breakdown of the triglyceride is then easily absorbed actually into the cell. So we get micelles which come into contact with microvilli, and the monoglyceride plus the fatty acids pass through the cell membrane. Because what are our cell membranes made up of predominantly? Phospholipid bilayers, fats. So you take some fat and you mix it with fat, and they all mix together just fine and dandy. And so that's why we can actually then, as long as we can get them into contact, and they're small enough, and into contact with the cell membrane, they'll get in there and they'll wiggle themselves all the way through because it's easy for them to do that. And then once we're inside the cell, it's a really strange thing. We then reassemble the triglyceride. And the triglyceride is going to then associate with cholesterol and some proteins. And when it does this, it creates now what's called a chylomicron. So we have two terms here to memorize, micelles and chylomicrons. They're both associated with our lipase and lipid digestion process, and you have to figure out on what side of the cell are we going to find micelles, which is the mucosal side of the cell, and chylomicrons, because the chylomicrons are going to be exocytosed out of the basal side of the cell. And it's going to go into the CT. And then because they are so big, and see, the reason they do exocytosis is even though they are chylomicrons, micron sounds really small, right? Even though they are chylomicrons, very, very small, they are still too big to enter into our blood capillaries. And so we have another vessel that will actually allow big things in. Do you guys remember the other vessel that's going to allow big things in? Lymphatic capillaries, which we now call lacteals. They're way too big to get into ordinary blood capillaries. But our lymphatic capillaries are great with the way they're actually made. They can actually open up a nice little area, and then the chylomicrons can go in. And one of the ways that you might be able to remember chylomicron is going into the lacteals or lymphatic capillaries. Do you remember we actually asked you to learn a term called cisterna chyli? So chylomicrons and cisterna chyli. Remember, that's lymphatic, and so that maybe will help you to remember that this is what we find on the basal side of the cell. And so then it will go from the lymphatics and get actually then placed into the venous side once we get to the internal jugular and subclavian up in the neck area. Okay, absorption. Absorption of all of the material in our small intestine is 80% complete before the ileum. So what that means is all the stuff that we just talked about, 80% of the stuff is occurring in the duodenum and jejunum, and so the ileum is for the leftover stuff for absorption. What's really interesting, the ileum is longer than the duodenum and jejunum combined and is only responsible for 20% of our absorptive needs of the foodstuffs that we take in. The other thing that's important in that area is 2 vitamins are also, for the most part, absorbed in the small intestine, except for those that are made by bacteria from the large intestine. So that's that chapter. We're off to the next. The nutrition and metabolism. We have courses on campus that are nutrition courses, so I won't cover much in the way of nutrition. I am actually only going to cover very, very basic nutrition information here. And you see it all on this just one short area of this page. So if you want to know more nutrition, take the nutrition course. The study of obtaining and utilization of the nutrients from our environment or not for growth and life. So that's what the definition of nutrition is for us. And our nutrient needs are going to fall into 2 categories, macronutrients and micronutrients. And it's basically how big it is that we need to actually take it in order for us to actually utilize it. So macronutrients consumed in relatively large quantities for our needs, and macromolecules, and micronutrients, small amounts, and we do need our micronutrients or obtain it from a wide variety of foodstuffs. Because macronutrients are just 3 main categories, carbohydrates, lipids, and proteins, which is what we just talked about for absorption and stuff along that line. Our carbohydrates are saccharides. Our proteins, we know, are amino acids for the monomers, and our lipids are, we can actually use a generic category called hydrophobic macromolecules. Hydrophobic means they sure don't like water, and we know fats and water actually don't mix. So that's a very simplistic definition of them. As far as saccharides, they are either simple, which is a monosaccharide, or complex. We have a tendency to obtain them in the dietary form of starches or fiber. And we use them for energy, or we could say fuel, cellular fuel. That's their primary utilization by our systems. Lipids, again, hydrophobic molecules. We use them for energy storage, cell membranes, and hormones. Energy storage, the most common lipid for energy storage are TGs, triglycerides. That's what our little fat cells all have in them. And for cell membranes, you guys know, phospholipid bilayer. And do you guys remember what category that is lipid-based for our hormones? Cholesterol, correct. Absolutely. Proteins, the monomer is amino acid, and we make polymers or polypeptides to create proteins, and our proteins are utilized by us for either structural reasons or functional needs. And typically we find them as globular in their shape. hemoglobin, for example, myoglobin. So they have a globular look to them because it's the shape of that molecule that is important in bringing various things together and working for us, even enzymatically. So macronutrients, carbohydrates, lipids, and proteins, need to get these into our body in large quantities to take care of us. Micronutrients, small amount. And of the micronutrients, two main categories are vitamins and minerals. And we're very simple in what I want you to know about vitamins. We have two categories of vitamins. They're water soluble or fat soluble. Water soluble are our B's and C's. And so if you ingest too much vitamin C, you just pee it on out. So that's that water soluble nature of it. Fat soluble vitamins are A, D, E, and K. And in order for these vitamins to be properly absorbed into your system, they need to be actually consumed with some fat in your meal. And so I typically say a high-fat meal, but that's where they're going to actually, their absorption is going to be very important for you. So if you take because we live in the northern climes and we get vitamin D deficient in the wintertime, if you're taking a vitamin D supplement, it's best to take that vitamin D supplement with your meal that actually has some fat in the diet, not by itself, for best absorption. So for best absorption, fat-soluble vitamins should be taken with some sort of fatty food. We will classify our vitamins as either essential or non-essential. In other words, they're essential. You have to get it from your environment, i.e. your diet. So the non-essential ones are interesting is that we can actually make them. So essential means we can't make. Non-essential means we can make. And we have a tendency to recycle that which we can actually make for ourselves, which is really interesting. We're going to look a little bit more at the non-essential ones because we use them as cofactors in our chemical reactions, our redox reactions, which we're going to talk about next. Minerals, well, we can't make minerals, so we have to get them from our environment, and they are therefore essential for us. What are some of the minerals or ions that we have actually talked about a lot throughout A&P? Sodium, potassium, calcium. I love it. You guys are doing great. Any others that we've talked a bunch about? Because these are the ones that we actually need in more than what are called trace amounts, because there's trace minerals which we don't need very much of, but then these guys, we need a lot of these in order to function properly. Iron is actually a trace, but that's a reasonable thing to say because that is indeed what most of us think. We forgot about the chloride ion. So chloride is actually also a part of this story. And because of ATP, phosphorus. So because P in ATP is phosphorus related, so we also need our phosphorus. And you may not know it, but Mg stands for magnesium. So Mg, magnesium, is also one. And the very last one is sulfur. You don't realize it, but I know we don't realize it, but it's actually part of amino acid structure. A lot of those have sulfur in their structure. So that's it for nutrition needs. And we're now moving to metabolism. Metabolism is defined as the sum of all biochemical reactions in the body. And anabolism, catabolism, oxidation, and reduction are all various chemical reactions that occur in our body. The two main ones that we're going to spend just a brief amount of time with here, anabolism and catabolism. Anabolism, building larger molecules from smaller molecules. And this is where I like to say using amino acids to make proteins. That is an anabolic process. And I like to use that as an example of anabolism because of anabolic steroids that certain people like to use because they're typically bodybuilders, correct? They want to get bigger and stronger, and so they'll take anabolic steroids to actually make things bigger. And I think that's a great example for anabolic reactions. Catabolic reactions are the opposite of anabolic reactions. We break large molecules into smaller substances, and we are going to spend a lot of time with that with glycogen hydrolysis to make glucose. And then we are going to have glucose hydrolysis to make our pyruvates. So that is a catabolic reaction that we're going to take a look into, because that's going to be the initiating process for our generation of ATP and the steps that we actually utilize to actually make a lot of ATP. So that's what this is all about. I don't want to go into oxidation and reduction yet. I actually want to talk about anabolic and catabolic reactions. The sum of these two is what the basic definition of metabolism is. And so you will hear people say, I have a high metabolism or I have a slow metabolism. And what they're telling you, they don't realize it, is that they are more anabolic or more catabolic. And so when somebody says, I have a slow metabolism, they have more anabolic reactions. I know it's hard to say. Anabolic reactions and catabolic reactions. And when somebody says, I have a high metabolism, that means they have more catabolic reactions kind of going on versus anabolic reactions. And the interesting thing is when somebody says, I have a slow metabolism, they're typically saying it because they have a problem with weight, correct? Well, the important thing, evolutionary-wise, for people who have a very slow metabolism is that they are designed to survive. And they are, our species has, before we became so modernized and everything, we went through long periods of starvation. And so those individuals who, quote, have a slow metabolism, honestly were the ones that actually carried us through various starvation periods. And so they are, you know, one of those nice things that you can say is, well, you are just definitely born to survive. They may not appreciate that comment, but you can definitely realize, thank you for having a slow metabolism, because it is your forefathers that allowed us to be here, because we did. We went through long periods of starvation and then periods of gluttony because you got around the food source and you just ate as much as you could in order to actually then build those reserves so that you could again go through starvation processes. So starvation is not foreign to our systems, except now, right? Who starves themselves anymore? Some people think they're starving themselves if they go 24 hours without a meal. And I'm just going, oh, you got to be kidding me. You know, there's plenty of food around you and you just didn't have time to eat. But starvation actually is a normal part of actually our physiology as we actually developed. Now let's talk about oxidation and reduction reactions. So we're going to spend a lot of time now, from now on, with oxidation and reduction reactions. And like the name, oxidation, doesn't that sound like it involves oxygen to you when I say oxidation? So when a substance is oxidized, it indeed will gain oxygen when it gets oxidized. But we are more interested in the flip side of this definition, which has here losing hydrogen. This is what we are more interested in our oxidation and reduction reactions. So oxidation, remember, something gets oxidized, it gains oxygen, but actually more importantly, I want you to remember it loses hydrogen and it loses electrons. That is key to everything else that we are going to be actually working on as we go through our cells and mitochondria and the reactions that they undergo in order to make ATP. So oxidized substances lose hydrogen and they lose electrons. So then reduction is the opposite of that. If you could get one memorized, then you know what the flip side of the other one is. So reduction is losing oxygen or gaining hydrogen plus gaining electrons. That is really important because that is what oxidation and reduction reactions are all about. And we typically use a term called redox when we're talking about them because if one gets oxidized, something else gets reduced. So they're coupled. I want you to understand oxidation and reduction reactions are always coupled. If something gets oxidized, the other thing gets reduced. And that's where cofactors come in. These are chemical structures that reversibly hold the hydrogen and electrons. So they will lose hydrogen and electrons or they will gain hydrogen and electrons. And so these are the guys that are actually going to be in our redox reactions. NAD is based upon niacin, that's a B vitamin. FAD is based upon riboflavin, which is also a B vitamin. And so these two cofactors are going to be carrying hydrogen and electrons throughout these various biochemical reactions to help us make ATP. So these are the big players in the generation of ATP. The mechanism of ATP synthesis, we have two main ways that we can actually make ATP. And this is what all this next stuff is all about that we're going to go over. Substrate level phosphorylation or oxidative phosphorylation. Substrate level phosphorylation, I want you to understand phosphorylation is the transfer of phosphorus or a phosphate group. So P is in there. Phosphorylation, P is in there. So substrate level phosphorylation is where we are taking a phosphate group is transferred to ADP. So if we take a phosphate group and add it to ADP, we will get ATP. The phosphate group is being carried, so to speak. It is being the carrier for that phosphate. So there is a carrier molecule for this phosphate. PO4 is what I'll put down for that. So there's a molecule that has this phosphate group attached to it. It comes across ADP and it gives ADP the phosphate, which makes then ATP. So there's all kinds of areas where substrate level phosphorylation occurs, but it is predominantly in the cytoplasm of the cell. Oxidative phosphorylation sounds like we need oxygen somewhere in the story, and indeed, oxygen is going to be called the final electron acceptor. In this process that occurs in the mitochondria. Oxidative phosphorylation occurs in our mitochondria only. And what we are going to utilize is we are going to create a concentration gradient. So chemiosmotic, do you guys remember osmosis? Didn't we have a concentration gradient of water? Well, this isn't going to be a concentration gradient of water, but it's going to be one of those atoms of water, and it's going to be the hydrogen ion, which is part of what a water molecule is. So it's going to be the hydrogen ion. We are going to create a concentration gradient of hydrogen ions to actually generate ATP. And let's take a look at this portion of a mitochondria down below here. This is our outer mitochondrial membrane. Remember, mitochondria are double membrane structure. And this is our inner mitochondrial membrane, and sometimes it's referred to as having cristae. Remember any of that maybe? Yeah. So what we are going to do is we are going to actually have, if we're going to create a concentration gradient of protons, we're going to need some pumps. You guys follow me with that? Because if we want to create this concentration gradient, we're going to create some proton pumps, because that's what these guys are. All those guys in that membrane are actually proton pumps, and pumps always work against a concentration gradient, correct? They try to take a substance and move it from an area of low concentration to an area of high concentration. That's why we have pumps, right? Because we can use diffusion if it's the other way around. So these are proton pumps. So they're designed to move protons from an area of low concentration to an area of high concentration, which is in this intermembrane space. So between the outer and inner mitochondrial membrane, we are going to force a bunch of protons in here and create a concentration gradient. Then those protons, which we are forcing through to make it high in this area, will want to actually diffuse if you give them a chance, correct? And they will want to diffuse, and they have a portal, so to speak. And this portal is ATP synthase. And ATP synthase is the portal for hydrogen ions to flow through. What's really interesting about this interesting protein in the inner mitochondrial membrane, when hydrogen ions flow through that, they act like a water flowing through a water wheel. And remember, when water flows through a water wheel, it makes it move and it generates power, correct? And this causes enough power to actually create a bond between ADP and inorganic phosphate. And so right here is what we are going to be actually looking at in mitochondria. Substrate level phosphorylation is not an inorganic phosphate process. P(i) means this phosphorus is not attached to any sort of carbon-containing molecule. And so we are going to use ATP synthase, because doesn't it sound like ATP synthase makes ATP? ACE is an enzyme synthase. So this ATP synthase enzyme, which makes ATP, will need the power of a concentration gradient of protons to flow through it so it can actually make ATP. So that is what oxidative phosphorylation is. And in this process, we don't see it right here, but in this process, we are going to then actually use electrons. And they will actually go to oxygen and we'll make water with that. But that's too much of the story for right now. Whenever we have a pump, what do we need in order for a pump to actually work? We have always used the fuel ATP, correct? But that doesn't make sense if we're trying to make ATP with this process. So these proton pumps don't use ATP for their fuel. They use the energy from electrons. And so that's what this is all about with oxidative phosphorylation. This process will take electrons, because remember I just talked about hydrogen and protons? We are going, electrons for NAD and FAD. We are going to use those molecules to carry hydrogen ions and protons, electrons, I'm on the wrong side of the charge there. We're going to take protons and electrons, because isn't that what a hydrogen ion is? Isn't it a proton? Yeah. We're going to take protons and electrons, and we're going to use those protons to pump them through our proton pumps, and we're going to use electrons to actually power the whole process. So that's what we're actually dealing with in our formation of ATP. We're using a different source of energy for our pumps. So we are going to couple ATP formation with proton movement. And Most of our ATP is made this way. Right down here, major source of ATP production. And remember, carbohydrate is our major macronutrient that we utilize for fuel, so that's what we're going to go into. C6H12O6 is glucose. Plus 6 oxygen molecules will give us 6 water molecules, 6 carbon dioxide molecules, and we are going to figure out how much ATP ultimately we can get when we break down glucose. There are 3 main phases and 1 not so main phase in this glucose oxidation process. So this is going to be a catabolic process. We will talk more about glycolysis. This is a series of 10 steps resulting in the splitting of glucose into pyruvate, and I'm not going to make you learn all 10 steps. But I want you to know I'm saving you from 10 steps. So the few steps that I want you to know, I want you to know. Okay. Glucose is 6 carbons. Remember, glucose equals 6 carbons. Pyruvate equals 3 carbons. So how many pyruvates do you suppose we're going to get from 1 glucose? 2. And that is indeed what we get. This occurs in the cytoplasm, does not require oxygen, and is considered an anaerobic process. This is why we need oxygen, people, with oxidative phosphorylation to make the most bang for our buck for ATP generation. This is why we actually have respiration, so we can get oxygen for the other one that we're going to get to at the end of this. With glycolysis, we will get a total of 4 ATP produced, and this is called substrate level phosphorylation. So there's a molecule that has a phosphate group attached to it, and it's going to give it to ADP to make ATP. We will also produce, very important, 2 NADHs. And that's part of what NAD is all about. When you see NADH, from now on, remember we have NAD, and we are going to then get NADH. I want you to realize that is an H, that is a proton plus an electron process. So NADH is always a proton plus an electron that this NAD is carrying. One of these is oxidized and the other is reduced. Which one of this is this? Is that oxidized or is that the reduced form of that molecule? What's our definition of oxidation? That's not oxidized. It's the reduced form of that molecule. So this is reduced, and so therefore what must the other be? Oxidized. And that's what's going to happen. NAD can carry protons and electrons. When it carries protons and electrons, it's reduced, and when it gives it up, it's oxidized. That's why they call them redox reactions, one or the other on either side of that arrow. Now, we want as many NADHs as we can get, because we can get a lot of ATP from NADHs. And if it's produced in the cytoplasm, we need to get it into the mitochondria where that electron transport process occurs so that we can use them. We will get them into our mitochondria via 2 pathways. One is called the malate shuttle, and the other one is called the glycerol phosphate shuttle, or sometimes glycerol P shuttle, or GP shuttle. So that's because it's easier to just write P for phosphate for the time. One of them gives us more ATP than the other. So the malate shuttle, if we put our NADHs inside the mitochondria via the malate shuttle, we'll end up with more ATP than if we put our NADHs in via the glycerol P shuttle. And what's important here is it's important that you realize mitochondria will have one of the two shuttles. It doesn't have both. It has one of the two, and a cell will only have mitochondria that has only one kind of shuttle. And if you are a mitochondria that produces a lot of ATP versus one that doesn't produce as much ATP, you might find yourself in a different type of cell. Which mitochondria would you have in a heart muscle cell, and which type of mitochondria would you put in a skin cell? Which one? Yeah, the malate shuttle would be more often found in the mitochondria of heart muscle cells, and then the glycerol P shuttle would be more often found in those cells that just don't need as much ATP in their ordinary everyday functioning. So you have to realize a mitochondria doesn't have both. It has one or the other, and a cell doesn't have both type of mitochondria. It only has one or the other. One of the reasons why you need to realize that a cell only has one type of mitochondria is mitochondria produce themselves. So mitochondria reproduce. And so that's inside our cell. There was one mother mitochondria, and it actually came from our mothers, by the way. There's one mitochondria, and it will reproduce itself. So the shuttle that it has is the only shuttle those mitochondria actually have. Okay. The next thing is that we're going to look at is a step called the intermediate step that's not considered one of the main phases of glucose oxidation. So therefore, we say it's not part of glycolysis or the TCA cycle. And in this intermediate step, we will take our two pyruvates and we will turn them into two acetyl coenzyme A's. And that's how we abbreviate it. Acetyl or acetyl coenzyme A's. The important thing is pyruvates, remember, are 3 carbons each. Well, acetyl or acetyl CoAs, we've changed that into a 2-carbon chunk. In order to do this, we will have some byproducts. We'll have some carbon dioxide and we'll have some NADH. This step is actually a transition step from our pyruvate into our mitochondria. And so this NADH actually ends up in the mitochondria, and we don't need to actually have a shuttle. The only time we need a shuttle is for the NADH produced by glycolysis. Krebs cycle, or the TCA cycle, occurs inside the mitochondria, and the area inside the mitochondria is called the matrix in the mitochondrial cytoplasm. Sounds like we're getting a good rainstorm right now. The acoustics in this room are always fascinating to me. They're never what you'd actually think. But what's important with the TCA cycle, that's where our acetyl-CoA will then enter this cycle, enters the cycle. And a cycle sounds like a circle. And indeed, it is a circle, and it occurs over and over and over and over again. As long as you feed it, it will actually continue to go around and around the wheel, so to speak. And for each acetyl coenzyme A's that we put into the cycle, we will end up with 1 substrate level ATP. So for a glucose molecule, we get 2, correct? We will end up with 3 NADH, and that's, remember, this is for each. So we'll multiply that by 2, so we'll end up with 6, ultimately for glucose. And we'll end up with 1 FADH for 1, so therefore 2. And FADH is like NADH. Most of the literature has it as FADH2. It just tells you it's carrying more hydrogen ions. And we also like that because we can get more ATP from FADH2 than we can from substrate level phosphorylation, but just not as much as we get from NADH. So NADH is the star of the story. And that brings us to the next biochemical process called the electron transport, or ETP. It occurs on the inner mitochondrial membrane, because remember we have those pumps inside the inner mitochondrial membrane. And what we have here is we have a series of proton pumps that are fueled by electrons. And the materials for proton pumps and electrons come from NADH and FADH2. So we'll get our protons from NADH and FADH2, and we'll get our electrons from NADH and FADH2. So that's what's important that you realize. We got some proton pumps and we got some different kind of fuel, and those guys are carrying the stuff in so that we can actually ultimately create ATP via this chemiosmotic process or utilization of ATP synthase. So NADH and FADH both power the electron transport process. And our cytoplasmic NADH will come in to this process. If the malate shuttle is used, the electrons and protons are dropped off at the proton pump called FMN. If we're using the glycerol phosphate shuttle or the glycerol P shuttle, the electrons and protons will be dropped off at CoQ10. Have you guys ever heard of coenzyme CoQ? Yeah, there's actually people who will take supplements for CoQ10. So they'll come in at CoQ or CoQ10, and oxygen will end up being the final electron acceptor, and ultimately from this process we will make our water. So you have to memorize this entire picture, and you have to be able to create it from memory. All of this here. This is how I recommend you do it. I recommend you break it down in steps. So the first step, if you take a look at your picture there, is called glycolysis. Where we take glucose, which is 6 carbons, and we create a split, and we make a molecule called DHAP, and the other one is G3P. What's important about this step is that you see there's a couple of P's there. And so in order to actually create ATP, we need to put a little ATP in as starter money or starter fuel. And so we will actually take 2 ATP and put it into the process so that we can get our molecules that have phosphates now attached to them, and we'll end up with 2 ADP. DHAP is enzymatically changed to G3P. Remember, there's 10 steps here, and I'm only making you guys learn these 3 steps, and not all the molecules or enzymes are responsible for this. And G3P is what will ultimately make pyruvate. DHAP is 3 carbons. G3P is also 3 carbons. And pyruvate, as we know, is 3 carbons. Now, the important part here is that when we take G3P and make it into pyruvate, we actually make some ATP in this process. So we started off using ATP to get pyruvate. We'll end up making ATP to get pyruvate in this step. And because we're going to have a couple of G3Ps, we're going to end up with 4 ADPs giving us 4 ATPs. And that's because we're remembering we have 2 G3Ps. What's also, because remember I said in glycolysis we get some NADH. This is also the step when we make ATP where we actually make some NADH. So we will take NAD, and because we have 2 here, we'll have 2 NADs, which will give us 2 NADHs. So whenever I say NADH, I'm talking about something that's carrying protons and electrons, which is H plus and E's, right? So practice this until you can actually do it from memory. Then with our pyruvates, we end up with how many pyruvates from 1 glucose? 2. So let's put 2 here so we don't forget that. And from pyruvates, we're going to go into the intermediate step. And we want to make acetyl-CoA. So pyruvates will then help us to make acetyl-CoA, which is a 2-carbon molecule, and we'll get 2 of them, correct? So let's put 2 there. And when we go from a higher number of carbons to a lower number of carbons, the way we do this is by producing carbon dioxide. So this process is going to give us CO2. How many CO2s are we going to get from this process? 2. And whenever you see carbon dioxide being produced, you will also have the production of NADH. In order to have the production of NADH, and you have to put NAD into the process, and we will have 2 NADHs, just like we have 2 carbon dioxides. Now, we produced NADH up here, correct? And we are producing NADH here. So you do have to remember the other NADHs, but you can kind of lock this step in your head. Every time you see a carbon dioxide produced, you will always see an NADH produced. And you will see that the following chemical reactions will actually bear that out. We'll stop here, and I am going to actually make a recording of the completion of this chapter for you guys to review over spring break. Because chemistry and discussion of chemistry in lecture is really boring, isn't it? And so I'm going to make a boring lecture that I don't have to look at your bored faces. And so when we come back after spring break on Tuesday, please, the first 5 minutes of class, please ask me any questions that you want to about these biochemical processes, okay?